So we're going to look at an example here of how to implement the bisection method. We're going to work it all the way through. Right? We'll start from an equation with a required level of accuracy for our answer, and we'll work it all the way through to a final approximation that meets the requirements. And I'm really only going to do one example. One thing about this bisection method is that once the requirements have been met, once you've got a continuous function and it's got an opposite sign at the endpoints of an interval, it's largely foolproof. There really isn't anything that can go wrong. You'll see as we look at some of the other methods, even in just this equation solving chapter. Yeah, there are methods where you need to be aware of potential pitfalls and so forth, but this bisection method really just plain works. Right. So when I'm solving one of these, the first thing I like to do is see if I can get a quick sketch of the graph. Excel, there's all sorts of online programs that'll do this, or your graphing calculator, because this is a good way to pin down what our starting interval is going to be. Look at this function. Once we've got the graph, you can see, right away, it's negative at 0 and positive at 1. Right. So that's the interval we're going to use for our starting interval. And I need to take this thing that I've got right here and turn it into an actual equation. So what is an equation? But I'm going to set it equal to 0. So I'm going to make this e to the 2x minus 2 equals 0. And this e to the 2x minus 2, that's going to be the function that we're going to use in the method. So let's see how this works. I've got my initial interval, 0 to 1. And I calculated the value of the function at each of these points, and we can see, yes, we did get a positive 1 and a negative 1. Then I calculated the midpoint and the value of the function at that midpoint. Now, this value at the midpoint is positive, so I'm looking back. This was my previous positive function value, and that came from that endpoint. So it's that endpoint that's going to be replaced by, and you got to be careful here. This is an area where it's a very common mistake. That endpoint gets replaced by the midpoint. So my second interval is going to be from 0 to 0.5. A common mistake, people will put this function value in there instead. Right? It's not the function value, it's the midpoint. And now we just do it again. F of 0 is still negative 1. You calculate f of 0.5. The new midpoint is 0.25. And you calculate the value of the function at 0.25. Come up with a new interval. Keep repeating. Right now, I went and worked all of this out in advance because working out these numbers is pretty tedious. I did this in Excel. It was pretty straightforward to do there. And it was easy to copy and paste the results over here into the slides. If you do this in another computer program, Java, C, Python, whatever you're used to using, that's great. Like I said on the last lecture, I strongly encourage you to actually try to implement these algorithms. You're really going to understand them a lot better once you've done that. So just to kind of go through this a little further, you can see this process is continuing. Here on the third row, so we just did the second row, right? In the second row, the function value is negative. The negative endpoint was f of a, so it's a that got replaced by the midpoint. Got a negative value here. So again, it's the negative endpoint, right? That is still a that got replaced. All right, so how did I know I was done? Let's look at the function values here. I'm asking for 10 to the negative second, right? That's 2 decimal places worth of accuracy. So I'm looking at the first 2 decimal digits, 0.5, 0.25, 0.37. You notice they're changing, right? 0.43, 46, 45. Then we get to here, they're the same. Right? Once those 2 decimal digits settle down, as it were, we've reached the level of accuracy that we need. So at this point, I would say my solution is this value here. So what is that error estimate formula that we calculated have to say about this? Is our results here matching up with what that says we should expect? Remember, the error bound says the error must be less than or equal to b minus a over 2 to the n. So we can use this, if we know the level of accuracy we need, we can use this to actually calculate the number of iterations, the number of midpoints in this case, that we should have to calculate to get to that level. All right, so let's do that and see if our result is consistent with what we're seeing here. All right, so our a and b were 0 and 1, so 1 minus 0 over 2 to the n, and I need this error bound to be at most 10 to the negative second. All right, well, this is 1 over 2 to the n equals 10 to the negative second, which is 2 to the n equals 100. Then you take the log base 2 of both sides, and you get n is approximately 6.6. So this is saying that we need to do at most, maybe we get lucky and it takes less, but if we do at most 6.6 calculations, that many midpoints, we should have the level of accuracy that we're looking for. Now, obviously, we can't do a fractional number, so I would round this up to 7. Did that happen? Right? Did we get the level of accuracy that we needed within 7 midpoint calculations? Well, 1, 2, 3, 4, 5, 6, 7. Yeah, we did. And by the time we got to the 7th midpoint, our answer was accurate out to within 10 to the negative second. Now, since I was doing this I hadn't pre-calculated that, right? And I was doing this manually, as it were. Yeah, I didn't know it was going to take me 7, so I had to go one further. But that was just to confirm it. Right? I needed to go one further to confirm that I was actually at that level, and the second 2 decimal digits had become fixed. Right? If we had done this in advance, then I would have just said, yeah, okay, I'm going to stop at 7, right? Because I know I'm where I need to be. So this brings us to the end of our discussion of the midpoint method. In the next lecture, we're going to look at another method for approximating the solutions of equations. It's called fixed point iteration.